I'm first going to talk about a bit like overview about what is object tracking. And then I'll talk about how do we measure a tracker, how does it perform. Then I'll go over a few papers from, again, from CVPR, from the latest CVPR. So let's start. So what is object tracking? Basically, object tracking takes a short video clip with one main object that it wants to track. The clip is annotated using a rotated or regular bounding box on every frame. And the object tracker is given only the first bounding box from the first frame. And then you need to produce a bounding box for every single frame at the rest of the clip. You can see here an example from one of the benchmark, of the object tracking benchmark. You can see that there are some distractors. Sometimes there's lots of occlusion. The object can change scale, can change location. So it's pretty much a very hard task. Just look at this video, it's interesting. Lots of aspect ratio changing, scale changing, orientation, etc. So how do we measure object tracker? So the basic methodology is a reset-based methodology, which means that the object tracker is running on the frames, and every time it loses track, it means that the IOU is 0 compared to the ground truth. Then the object tracker is reinitialized 5 frames after the failure. This way, we don't punish a tracker that missed the object at the first few frames of the clip. Maybe in the rest of the clip, you can track really good. So this is the basic methodology of testing. And the metrics that we use are 3 main metrics. The first one is accuracy, which is basically the average overlap between the tracked bounding box and the ground truth during successful tracking periods, meaning the IOU is larger than 0. The next metric is robustness, that counts how many failures we have during a tracking clip. And the last one, the expected average overlap, is basically a principal combination of the accuracy and robustness, because we want actually one metric to rule them all. And it estimates the average overlap to the ground truth on all the frames, including the 0 IOU frames, on short-term sequences of different length. So they have like lots of different clips, different length, and it's average on all the frames. So later, when we compare the papers, we'll see these matrices. Okay, so now let's go to the first paper I want to present. It's the SiamRPN++. It's basically a Siam network for object tracking. There's a whole family of trackers that are based on this method. In this paper, they use 2 ResNet 15 networks, one for the reference frame and one for the search frame. They take features from 3 different places from the backbone, and they combine them to get 2 detection heads, one for the classification and one for the tracking. And in the end, they use K anchors, which is they spread it 1 for aspect ratio, 1 for scale, and 5 aspect ratio. So basically, it's an object detection network that its model is learned from the target frame, meaning the initial frame where we have ground truth. So how do they combine the networks? We have 2 networks. We want to combine their features. So they use the SiamRPN block. It's a regular standard block, which apply correlation between the reference feature map and the search feature map. What they use a novel layer. This is one of their new things that they came up. They use a depth-wise correlation layer, which is, and they use different depth-wise correlation layer, one for the regression and one for the classification, because they want to uncouple these two tasks. So what is the depth-wise correlation layer? So it basically takes two feature map, and it does a correlation channel by channel. Each channel do the correlation by itself. They don't combine between different channels as maybe a regular convolution would do. The spatial size of the reference frame is usually smaller than the search frame because maybe the object move a bit, so we want to find it in a larger search area. And one of the advantages of this layer is that it's 10 times fewer parameters than previously used layer, the up channel cross correlation that was used in SiamRPN. So it's much faster and it gives better results. And another interesting property of this layer, that the object of the same category actually get high respond in different channels. Meaning that, for example, for the car, you can see in the two middle columns, the high response, it's in channel 148, and the other channels are suppressed. And for person, we have high response in 222, and for face in 226. So there is some interpretation of the feature map. Another improvement that they add to their object tracker is the shift invariance in padded network. Most Siam-based tracker don't use padded network. They use AlexNet, for example. Because padded network breaks the translation invariance property of the correlation. Because in the edge of the search region, you have zeros, so it's break the translation invariant. But we do want to use padded networks. They are more accurate and they can be deeper. So what they do, they use large random shift augmentation during training, which wasn't done before, and they show here that it's mitigate the problem and they improve accuracy as you increase the shift augmentation. So this is another innovation that they present, and in the result here on a dataset called Brodmann17, they show significant improvement in accuracy and EAO. But the robustness is a bit smaller than the previous state of the art. Also, they run in real time, 35 FPS with the ResNet 50 backbone. They have another variant using MobileNet backbone that run in 70 FPS. It's all measured on GPU, of course. Okay, so here's a bit of an example of how the object tracking look like. I couldn't find a video of this specific paper, the SiamRPN++, but I gave this video of like their reference, their baseline. You can see the challenging task and the result that came up. So the next paper I'm going to talk, yeah.
It looks like a toy problem.
Sorry?
It looks like a toy problem. It is not a difficult task.
This one?
This one.
Well, maybe because the paper is white and it's mostly round. I don't know, but if I'll show in the last section a few other clips, and also in the first frame I show different clips. Yeah, well, later. There are different clips. There are lots of variety. That's the main problem of object tracking. It's not for a specific object. This clip specifically is on a paper bag, on a plastic bag, but it can be on a basketball player, on a car, or whatever you want. So, okay. So now I'll go to the second paper I want to talk. It's called Atom, Accurate Tracking by Overlap Maximization. They aim to improve the tracker accuracy compared to its robustness. And they use a two-stage tracker. They first do a coarse localization using a shallow classification head. And then they fine-tune the localization using a IOU predictor. The IOU predictor is trained offline, and the classification head is trained online. And let's look at it in high level at first. So in the initial frame, where we have the ground truth, they train the classification head using 30 augmented samples. And then they also compute some reference modulation vector for the IOU predictor. Later, I will explain how they use this modulation vector in order to predict the IOU. In the next frame, where they want to track the object, they extract feature using their backbone, and then they use the classification head for coarse localization. Basically, they get the X and Y of the object. Then they create 10 uniformly random bounding box proposal using the previous scale. They take the XY, they add the previous WH, and they add random noise to the bounding box to get 10 proposal. They fine-tune this proposal using the predictor IOU, and they fine-tune it using 5 gradient ascent steps. They have this Roy pooling, they gradient ascent to get a better localization proposal. They take the 3 best IOU proposal, average them to get the final result. So now let's go deeper. We have the backbone, the resonating was pre-trained on ImageNet, and it's act as a feature extractor. Now we have the classification head. This classification head is a two-layer fully convolutional neural network. It is online trained using Gauss-Newton approximation and conjugate gradient method. It's it's a complicated optimization technique that mostly work on convex function. That's why on shallow network it can work, but on deeper network it's much harder to apply. They fully train this classification head on the first frame, and they fine-tune only the second layer every 10th frame. They apply some hard negative by increasing the learning weight of samples where they have a distractor, meaning they have 2 peaks in their classification result. So they have the main peak that's supposed to be the object that they want to track, and another peak that is a distractor. Okay, so that was the classification head, and now we go to the IOU predictor. The IOU predictor uses a precise Roy pooling to crop the region from the reference frame and for the search frame. In the reference frame, it creates a 1-by-1 modulation vector, which will later be used in the search frame. They use it by channel-wise modulate the search crop. That means that every channel in the search crop is multiplied by 1 element from the modulation vector. They add additional fully connected layer at the end to get the final IOU. And it's trained offline using some tracking data set that taking 2 frames with some gap between them and train this network. They also show a result on VOT 2018. They also improve the accuracy and EAO compared to the last state of the art, but the robustness was a bit less. But the robustness is better than the SiamRPN that we saw previously. And they also run in real time on 30 FPS on a GPU. Actually, in the CVPR, the results here are worse than the SiamRPN that I showed previously. But on CVPR, they show a slide where they use a backbone of ResNet 50, sorry, which has much better result than the SiamRPN++. And they also have a new paper, which based on this one, which improved their tracker even more. So now we should see some of the result of their tracker. You can see here the aspect ratio changing and the scale changing. This tracking example is much harder than the plastic bag that we saw previously. And it's very impressive that the bounding box is pretty tight around the object. So that's what they aim for, and I think they got a really nice result. So now we're getting to the last two papers I want to talk about. I'm going to talk about them much more briefly. So the first one is target-aware deep tracking. Basically, what it does is also based on SIAM networks object tracking, but it adds this middle part to the basic SIAM network, and this middle part basically choose which channel are best to use in order to track the current object. For example, when we track the person, as we see in this example, this runner, we want to use channel number 10, number 100, and number 150. So we'll suppress all the other channels, and we use only this one. And if we want to track car, we use different channels. We use channel 70, channel 80, and channel number 1. So the middle part of this SIAM network, that's what it aimed to do. It aimed to choose the right channels in order to track the object. He asked which channel use. It's the feature space channels. It's the feature space, okay? You see, you see it's just added before the correlation filter, which combine the two networks. To choose the right channel, you use some gradient based. You compute the gradient on the first frame, and the channel that has the most gradient, you say it's the most significant, and he gets the largest weight. They show the result on VOT 2016, so we can't really compare them to the previous paper I talked about, but they also improve the result, the accuracy result, basically, and they're also running on real time. The last paper I'm going to talk about is the only one that is not deep learning. It's using a correlation filter, which is a big topic in the object tracking task. It's based on KCF tracker, if anybody knows it. It's a famous tracker. And the main innovation in this paper that they adaptively choose which part of the bounding box we need to learn from. For example, if we track a face in a certain clip and part of the face is hidden by some paper or whatever, so I won't learn from the hidden part. I will only learn only fine-tune the model using the non-occluded part. So that's what you see here. The face in the left part are not occluded, so they can learn from the whole bounding box. When she occlude the bottom part, so I don't learn the bottom part, I only learn the upper, and again in the right image. So they also improve results compared to previous method. They also improve the robustness, which we didn't see it before. And they also run almost in real time on GPU. So these are the papers I want to talk about. And for conclusion, I want to show, before I'll say the last notes, I want to show this graph, which is an interesting graph that maps all the object tracker that almost exists in the literature. And you can see that in the right part, in the top right part, it's all the correlation filter, mostly based on KCF that you see in large, which is a very popular one. And on the left part, it's all deep learning. And the left bottom part, it's all SIAMese-based object tracker. Then you can find the Atom and the SiamRPN++. I couldn't find the other two, so maybe it didn't put there. So to conclude, Object tracking is a vivid research field, lots of research and lots of hard tasks to solve. Correlation filter, the last paper I talked about, was dominate this world until a certain time, and I think that now Siamese network starting to catch up and get better and better result in real time. And they also have some new option they can offer, like Siam mask. They didn't get the best result, but they also offer a mask, like a segmentation mask of the tracked object, which is nice. And the last point I want to emphasize is that better understanding of deep networks can improve object tracking and overall task in computer vision. And if you take the paper I talked about, you can see that every paper said that each channel represents a certain object type. For example, the SiamRPN++, say you saw that the depth-wise correlation filter has different layer for different object. The reference modulation vector in the atom tracker basically apply a weight for each channel in the feature map using the reference frame. And the target-aware deep tracking, that it's the main innovation, that choose which channel to track according to the object type. So they all use basically the same technique, but in different way. That's about it. Thank you. Yes.
You mentioned the robustness measure several times. So what is it exactly? How it is calculated?
Well, I don't want to go exactly to how it's calculated, but basically it measures the amount of time, like the amount of times that the tracker lose track during a tracking session. Like I think it just count the amount of time and divide it by the whole amount of frames or something like that. But I'm not sure exactly how it's calculated, but it's supposed to measure how much time the tracker can continue tracking without need to be reinitialized. Any other question? Yeah. You get.
Yeah, you mentioned it. Thank you. You mentioned this when you calculate the measure of the accuracy, you don't want to punish if the tracker misses for a few frames and then gets back. It's kind of difficult for me to understand why would it come back except of some random noise, unless it's something very specific task of cars and you just jump from one car and not from another and back. Like in the case of this bag or in case of a dog which walks in the park, I mean, you miss the dog and you hit the grass. What reason would it have to get back from the grass to the dog?
When I talked about reinitialization, I said it's the benchmark, it's the testing. If you want to measure how the tracker is performed. So when you see, so you have a full control on the ground truth and the tracker. So when you see the tracker lose track, so the IOU is getting 0, so you stop tracking and reinitialize the tracker from the 5 frame later, because you don't want to punish the tracker if you lose track. It's a good methodology to mitigate some bias because of the data set. Any more questions? Great, thank you.